So far in this class, we've looked at mathematical descriptions of the dynamics of chemical and biological processes. And in addition to the processes, we've looked at the behavior of sensors, controllers, transducers, and valves. We've also developed some mathematical tools that allow us to describe the dynamics of these equations in the Laplace domain, including the idea of transfer functions. Now we're going to put all of those concepts together to describe the dynamics of closed-loop feedback control systems. We'll do this by going back and forth between mathematical descriptions of the process, an instrument diagram of the process, and a representation of it in the form of a block diagram. We'll begin by considering this stirred tank blending process. The feedback control loop contains multiple elements, including the process, the composition analyzer transmitter, a controller, which we'll assume in this case is a PI controller, an IP transducer, and a valve. Now, connecting these, there are signals or process variables. So the process generates a composition X of the effluent stream and the mixture inside the tank. That composition X is measured by the composition analyzer transmitter, which produces a signal called X sub m, the measured value, which in this case will be a current signal that ranges between 4 and 20 milliamps. If we choose a set point that's a composition value, say a mass fraction, then that composition value also needs to be converted to the 4 to 20 milliamp scale inside the controller so that it can be compared to the measured value to calculate the error signal. The error signal will be used inside the controller according to the PI control algorithm to compute a controller output signal P that goes to the current to pressure transducer. The current to pressure transducer will convert that signal to a pneumatic signal to actuate the valve. Now the valve takes that incoming pneumatic signal and mechanically converts it to a flow rate, W2. And when W2 changes, that alters the composition or mass fraction of the fluid in the tank. So at each of these components, a signal coming in will be converted to an output signal with dynamics represented by a transfer function and a gain that may change the units. For example, the composition in mass fraction units is being converted to a measured composition, which is a current signal, by the sensor analyzer transmitter. Now we'll take each of these components and represent them with their respective transfer functions in parts of a block diagram. We'll start with the process. We've previously developed the mathematical model describing the blending tank and converted it to the Laplace domain. In this case, we're considering how deviations in the composition X are affected by deviations in the incoming composition of stream X1 and the flow rate of stream 2, or W2. This model shows how a linear combination of the two input deviations gives rise to deviations in the output. This can be represented in block diagram form, showing the two inputs on the left, the mass fraction deviation in stream 1 and the flow rate deviation in stream 2, each being fed into a transfer function. The products of the inputs and their respective transfer functions are then summed because these two paths are in parallel and they come into the summation block to give rise to the result, the deviation in X. In the block diagram, we label this signal here representing the deviation in X1 multiplied by its transfer function as X sub d, and this deviation here representing the deviation in the flow rate multiplied by its transfer function as X sub u. Here the d indicates that this is a disturbance input, and the u represents that this is a manipulated variable input. From the dynamic model of the process, we should already know what the gains and the time constants of these transfer functions are. K1 is the fraction of the total flow rate into the tank represented by stream 1, and K2 is the difference in composition between X2 and the composition in the tank divided by the total flow rate. Of course, the time constant is the residence time for the tank, V rho divided by W bar. Now we'll assume the composition analyzer transmitter behaves according to first order kinetics, so it's represented by a first order transfer function. the actual mass fraction of the solute in the fluid in the tank is converted to an electronic signal on a milliamp scale. But that measurement does not occur instantaneously. It occurs according to a first-order transfer function with a characteristic time constant we'll call tau m. Next, let's look at the block diagram for the controller. The controller actually has two inputs, the measured value coming from the sensor transmitter, and in this instrument diagram, we're also showing the set point. Now, often the set point is left out of the instrument diagram, but here we're showing it so that we can make sure we include it in the block diagram. We said that the controller would be a PI controller. So we know what the transfer function is relating the deviation in the controller output to the error signal. And we can represent that with this block here. Upstream of that, we need to compute the error signal from the difference between the measured value and the set point. And we do that by taking their difference. Now, since the measured value is on a milliamp scale, we also have to use the same gain that's used for the sensor transmitter to convert our desired composition set point to the same milliamp scale. So this conversion of the set point to the milliamp scale, finding the difference between the set point and the measured value, and computing the controller output are all done inside this controller represented by this single element in the instrument diagram. Next is an easy one. The IP transducer simply takes a current signal and converts it to a pneumatic pressure signal. Here we call the deviation in that signal P sub t prime to differentiate it from P prime, which is the controller output on the milliamp scale. To make that conversion, we simply need a gain for the IP transducer that converts the milliamp units to the pressure units. The conversion of the milliamp signal to the pressure signal occurs essentially instantaneously at the transducer. There's no time constant associated with this transfer function. It's simply a gain. Next, that pressure signal is sent to the valve where it modulates the flow rate. The gain for the valve describes by how much the flow rate changes for a given change in the pressure signal. This transfer function also contains a first-order denominator, so we're assuming that the valve does not act instantaneously. It actually takes time for the valve stem to move up and down when the pressure signal is changed. And that we approximate with first-order kinetics. We're using a time constant tau sub v. Now we can put all of this together to make a block diagram for the control loop. We'll start with the process, which combines the disturbance variable deviation x1 with the manipulated variable deviation w2 according to their respective transfer functions to give us the deviation in the controlled variable x. That controlled variable x is measured, and the measured value is fed back to the controller where it is compared to the set point to calculate the error signal, which is then used according to the PI controller algorithm to calculate the controller output signal P. The controller output signal is converted by the IP transducer to a pressure signal, which then goes to the valve, where the valve uses that pressure signal to modulate the flow rate W2. All of this is developed in the first section of Chapter 11 of our textbook, but when they assemble this block diagram in Chapter 11, they replace the measurement transfer function with a gain, Km, instead of a first-order transfer function. So that's inconsistent with the way the authors originally proposed that the sensor behaves. The gain for the sensor occurs on the left-hand side here, where the set point has to be converted to milliamps, and that is done without the time constant. But the actual measurement of the controlled variable does contain the time constant tau m. You need to be able to go back and forth among a diagram representing the process and the instrumentation, transfer function models representing each of the components of the instrument diagram, and a block diagram like the one shown here. Now we already know how each of the signals and variables represented by the arrows here are converted from one signal or variable to another using each of these individual transfer functions. And because we've organized them into the block diagram, in the next video we'll show how we can use the block diagram to develop other relationships among the process variables. This will enable us to answer important questions, like how does a change in the set point ultimately affect the composition variable in the closed loop system? Or alternatively, how does a disturbance input in x1 affect x in the closed loop system.